Okay, so recall in 2 dimensions, the expression dy over dx really gives us an instantaneous rate of change in a particular pair of dimensions, okay? So what we're talking about is delta y over delta x, and you're limiting those to 0, okay? In R3, though, you're going to be studying how z changes, all right? And we have to consider how z changes with respect to x and y. So in other words, how it changes with respect to x and how it changes with respect to y, see? So there's kind of 2 things going on. In other words, we need to find more than one derivative if we're going to understand a function's behavior. Okay, so let me just kind of explain that. Here's a random surface in space. Okay, that's just like a random sheet, some kind of weird surface. You saw a crazy looking one yesterday on the beginning of your notes. Right? So most likely the questions will ask, how does z change? Well, it depends on which direction you go. Okay? If you travel in a direction parallel to the x-axis, you'll be traveling along one of these red paths, you see. If you travel in a direction parallel to the x-axis, you'll be traveling along one of these red paths. But if you travel in a direction parallel to the y-axis, you'll be traveling along one of these green paths here. You see? See what I'm saying? So there's kind of 2 directions. So you have to be more specific. You say, hey, how does z change? You're like, well, which direction are we hiking? If this is like a mountain range, you want us to hike in the z direction? Or in the x direction, I mean? Or you want me to hike in the y direction? My paths look very different, you see. It might not even have the same type of equation. Traveling along an x might be like traveling along a parabola, whereas traveling along the y direction might be more like traveling along an ellipse. Weird things happen. Okay, so what we're saying is you can't hike in the z direction, but you can hike in either the x direction or the y direction. Kind of like a north and south or a east and west. And you're hiking through the woods. Okay? So you probably know that when you're hiking through the woods, if you just take a straight line, you encounter all sorts of weird things. You're supposed to kind of stay on the trail, but if you just hike in a straight line, you're going to like go through trees and bushes and cross a stream, and you might not even cross the stream at a right angle. You just kind of wade through the stream, like not even straight across the stream. You know what I mean? But we would like to study the rises and the falls of that path. Okay, does that make sense? Okay, so the red lines, you could describe all the slopes there by using something called dz dx. dz dx. How does z change when x is changing? Okay, so the red lines have slopes dz dx. The green ones have slope dz dy. Okay, and then there's those hikers that travel sort of in a hybrid direction. Those guys travel like in the both x and y at the same time direction, right? So maybe you travel sort of at a diagonal path. You're not traveling towards the x or the z. And you might want to describe that path too. Now that's a little more complicated. So if you're traveling along the x-axis, at least your y is consistent. As you're walking, your y's are the same always. Or if you're traveling along the green, at least your x's are like constant the whole time. Does that make sense? Okay. So we call these guys partial derivatives, and these explain the slopes. The red one explains the slopes along the red curve, but y is completely constant. Okay. And the greens describe the slopes along the y direction, but each x that you pick, when you pick a path and you start walking, that path has a constant x the whole time. See? So if you want to move in a hybrid direction, that gets a little more complicated, and you're going to have to start expressing your slope as a vector. So we're not ready for that yet. That's called a mixed derivative. Okay? We're not there yet. That's our next lesson, actually. But for today, we'll just travel in one direction, either x or y, and we'll check the rises and the falls accordingly. Okay? All right. So note, when we study derivatives in R3, we need to decide if we want to study derivatives where x and y are changing at the same time. That'd be for like a hiker who refuses to go either north or south or east and west. They just want to go in any random direction they please, which is kind of how we hike, right? You don't like hike east always. You pick your path, right? But what's going to happen there is you're going to have to take your path vector and you're going to have to sort of dot product it or something with your slope vectors, okay? So that's going to get complicated. Not ready for that. Let's just travel green lines, red lines today. Make sense? Hopefully that makes sense. Today we're finding partial derivatives then. Okay? df dx means the rate at which z is changing as x changes, treating y as a constant. And conversely, if we find df dy, it's basically like finding the rate of change for z as y changes, treating x as a constant, you see? Which is exactly what I was just saying a second ago. All right. Any questions on our goal here? Find the slopes along the green and red paths. Oh, question.
So df dx is synonymous with z and z?
df dx, I'll get to notation down here at the bottom, but z and f are the same thing. Remember how in two-dimensional world y and f are like the same thing, right? Y and f. I say f equals x squared, someone else says y equals x squared. Same thing. In this world, f means z. Very important. Your independent variables are x and y now. There's two independent variables. The dependent guy is z. Okay? So f means z. Good question. Glad you asked that. If there are more than three variables, you can find partial derivatives with respect to each one. Okay, so this is where it gets a little heady. But like, let's say you have a function called w, and it has an x direction, a y direction, and a z direction. Okay, so that's kind of a weird idea to you maybe. Like, how can you have more than just a surface, you know? But let's think theoretically. Okay, let's say you have like a heater in a room, right? And the heat is radiating out in all directions. Well, those field lines of the radiation are spherical, right? They're spherical. So you have a function that describes the radiation. If you pick like a point in the room, that radiation at that point in the room depends on how far in the x direction you are from the heater, how far you are in the y direction from the heater, and how far you are from the z direction from the heater. So it's like a three-dimensional sort of thing. That gets a little bit complicated. But what I'm saying is you can find three partial derivatives: df, df dx, df dy, df dz. You can have more than two partials. But on the mapping surface where we're taking a height, there's either east, west, or there's north, south. There's only two. But if you're traveling in three space, you have three possible things. So don't stress about it. Just follow the mechanics. It's actually really not very hard to do. But remember, if we're going to find df dx for this goofy function here, we're going to be treating our y's literally as constants. So if you see a y, think 1. Don't take, and if you're taking the derivative of a y and you're doing a ddx or anything, it's 0. So literally all the y's you see here are constants. So you have to really weed them out mentally, like you totally ignore the y's in this first exercise. And then when we do the second part, we'll ignore all the x's. So we're going to find df dx, circle that. X is sort of our variable, Anything else is not. Okay. Okay, so what's the derivative of x? 1. What's the derivative of cube root y? 0 is correct. No chain rule? It's 0. Y is a number. Okay? Okay, what's the derivative of ln x plus y squared? It's 1 over x plus y squared. Y squared. And we need the derivative of the inside. Well, what is the inside? Here. X plus a number. Remember, y is a number now. So, yeah, 1. The derivative of the inside is 1. So we don't need the chain rule there, do we? Or it doesn't yield anything. And lastly, what's the derivative of 1 with respect to any variable? 0. So the partial derivative with respect to x is 1 plus 1 over x plus y squared. Okay, that wasn't too hard. What does it represent? This equation will give you the rises and falls once you pick your y path. Okay? Because you're traveling in the x direction, which means you have a particular y that you're walking on. Okay, so you pick a y, say, hey, I'm going to travel along y equals 6. This is now 1 plus 1 over x plus 36. And that becomes your derivative. And you can, as you walk along the path and you get your different x's, you can start plugging in to get your slope of the hill. Okay? All right. But notice you're not surprised to find x and y in the answer because, well, the y needs to still be chosen so you can figure out which of the red paths you're traveling. And the x is there because as you walk forward along that path, the rises and falls happen. So
Don't be surprised to see two variables there. The next one, we're treating y as our variable, x as our constant, right? So I'm going to circle your denominator there so you know what you're doing. And notice the curly look on the differential. That was not a font choice, okay? d dx and d dx, like this, are not the same thing. The curly d's mean partial derivatives. Very, very important, okay? All right, so in this next one, we're going to treat any x's we see as numbers. So what's the derivative of x? 0, right? What's the derivative of cube root y? 1/3 y to the minus 2/3. You don't need a y prime because you're doing a d dy. So your variable of differentiation and your variable in this term is the same thing. Plus, and we get that 1 over x plus y squared again, but now we need to multiply by the derivative of the inside. So just 2y. And then lastly 0, because, well, 1. Derivative of 1 from any variable's perspective is always 0. So a totally different answer. And it represents the rises and falls if you travel along one of those green paths that I showed you a minute ago. You'll have to pick a green path, which means you'll actually insert an x. And then you'll have to watch it change as you walk along the y's. In other words, you'll then pick y's as you go. Okay, just so you know, there are tons of notations. This is where it gets really annoying. Okay? dz dx instead of df dx. Be ready to see that, okay? It means the same thing as df dx. dz dy. D sub x and d sub y. Very, very unfortunate notations. These notations look like Kramer's rule and matrix rule, where this means the determinant of, when you replace the right side into the first column, blah, blah, blah. But I'm just saying these have been used for other things in mathematics, so very annoying but very commonly used. It is awfully easy to write, d sub x, but it means the partial derivative with respect to x. F, or z sub x, interesting. Z sub x means the partial derivative with respect to x. Probably wouldn't have picked that notation myself, but it means the same thing as df dx. Okay? F sub x means the partial derivative with respect to x, and f sub x and y. These all mean exactly the same thing as dfxy dx and dfxy dy. They all mean exactly the same. So you have to go back to this page if you ever see something new and you're like, what are they asking me for? Go back to this page. It's probably just a partial derivative. Any questions on that? Okay, the rest of this is just practice, okay? It's just practice. So you could try it on your own, and I can even post the answers. I'll finish this recording later, too. But it really is just practice, and you have to be very, very careful to always think of y as a variable when you're doing a df dy and x as a constant and vice versa. So let's look at this next one. You're doing d dx. So x is your variable. If y here is a number, it's literally like, if y is 10, this is literally like 100x squared is what it looks like. 100x squared. The derivative of that, 200x. So basically, you'll differentiate the x squared to make 2x, but the y squared is literally a number, like a coefficient. So that just goes 2x y squared. Next is minus xy. Well, y is a number. It's like looking at 5x. The derivative is y. So you're only differentiating the x part. Okay, the next one says e to the xy squared, but y is a number. So this just becomes e to the xy squared. If you want to multiply by the derivative of the inside, so to speak, y squared is like a number. So that comes out. Plus, here we probably would want to use the quotient rule, right? Low d high 1 minus high x d low 1 all over low squared, and simplify. If you're going to do this with respect to y, this is going to be 2y x squared. X squared is just a number, you see. Minus x. This is a little bit hard to understand, but if you think of x as a number like 5, to survive is that x there. Sometimes it helps to think in numbers. This next term is an exponential, so you should just copy and paste that. And then look at the inside, xy squared. Let's see if x is a number, like 14. It would just be like 28y to the first. So basically it's 2x y plus, and then our product rule, our quotient rule again, all over low squared. Low d high is going to now look like this, x plus y times 0, because you're taking the derivative of the top, and the top is an x, which is a number, see? And then you go on to do minus high d low, which is x times the derivative of the bottom, and that's just 1. And then you simplify. Okay? So these are functions with two variables, and so you have to pick one to be your independent variable, and the other will just be like a number for now. And this brings us to our third case, which is in case you have a w function with three variables, you're just going to have to do three partial derivatives. First time you'll treat x like a number, or a function, then you'll treat y like a function, and then you'll treat z like a function, or variable. Yeah?
When you take the derivative of dxy squared, shouldn't it be minus 1 on the top?
Minus 1 on the top.
Because you usually subtract an exponent.
The derivative of e to the u is just e to the u
Oh yeah,
times du dx.
my bad.
Do you guys see any errors here? Okay, if you really are thinking of y as a number, right, then you kind of can just mentally ignore it. It's a little hard to learn, but okay. And question, last question?
You briefly said in the last one that
Uh-huh.
you have to do them separately, and then would you add them together? Or what would you do with the partial derivatives?
You keep them separate. They really are two different things. df dx and df dy, those are two derivatives. And so we expect two answers. We can't really put them together meaningfully. They're totally different dimensions. The rises and falls of the curves as we go in one direction, the rises and falls of the curves as we go in a different direction. When we try to put them together, they just look like vectors, so they're technically still separate. They're just written together. You know what I'm saying? So you can write your answers as, df dx, and then comma df dy, but it's still two numbers, kind of like an ordered pair, but it's two expressions. There is a problem there at the bottom using implicit differentiation. You just have to use your common sense on that, but I suggest that you watch the video. I'll finish this, and especially just watch that last example where I do the implicit thing, because the chain rule shows up there a little bit. So you guys are so good at derivatives. We shouldn't have any problem with this. The worksheet for... Okay, so now let's look at an example where we have three variables. Okay, so this function is called w because I didn't want to use z. Z is actually going to be one of my independent variables here. So the function's name is w, and then we have x, y, and z as separate independent variables. Okay, so if you look on the right side of this equation, you'll see that there are x's and y's and z's. All right? Okay, so when we find d dx, which is our first partial derivative, we'll treat everything except x as a constant. So what's the derivative with respect to x of 2x? That's just 2. What's the derivative of sine blah blah blah? It's always cosine blah blah blah, right? So just copy the blah 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 part. And then multiply by the derivative of the inside. Remember, the only thing that is actually a variable is the pi x, you see. Everything else is treated as a number, so like you can ignore these guys. So pi x, what's the derivative of pi x? It's just pi. So that's the derivative of the inside. I'm going to go ahead and put that in the front. Okay. Plus, now we're on to a log. Now this is a log base 10, so be careful here. It's log base 10. So you already know there's going to be a 2 in front, and you already know there's going to be a log base, an ln 2 on, an ln 10 on the bottom. Excuse me. The ln 10 is because of the base 10 log that we're trying to differentiate. Okay, anytime you take the derivative of a log expression, you do 1 over the inside, all of it. Then the derivative of the inside, remember only x counts as a variable. So you're totally going to ignore this term. And xy plus xz, you could just kind of think of that as x times y plus z. Y plus z is literally a number. So this is like 5x, you know. So if this was 5x, the derivative would be 5. Here, the derivative is simply y plus z. We'll put that on top instead of next to it. And now we're on to our last term. Our last term is right here. It is an inverse tan, so we always follow the same basic pattern. It's 1 over 1 plus whatever's inside squared. Then we multiply by the derivative of what's inside. So we have x, y, z, but the y and the z part is just a number, like, you know, 38 or whatever. So 38x would be, the derivative would be 38. So we're just going to put yz on top. That's sort of the derivative of the inside. Okay, let's look at this same problem. This time we'll take the derivative with respect to y.
Yes, there's one.
Okay? So let's start over. d dy. The first term is actually going to yield 0 because there's no y's in that term.
It's good.
Next is going to be a cosine, blah, 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 because you're differentiating, right? Plus 3y minus z. But the derivative of the inside is just 3 because everything except that 3y, everything except the 3y is considered constant. So there's just a 3 for the derivative of the inside. Plus, and then we have the 2 over ln 10 thing. And then the 1 over xy plus yz plus xz. But then you're going to look at the inside. The y's are variables. The x and the z are constants. So if you only have to look at these two terms, the ones that have y in them, and their coefficients are x and z, so you basically get x plus z. Notice the answer is a lot like the one above it. That's sometimes the case. And this last term is our arctan term. And the arctan term, we'll be treating this as 1 over 1 plus xyz squared. And the derivative of quote-unquote the inside is going to be xz. I'm sure you can guess the answer to the last one, but we'll fill that out as well. Okay, so for our last one, z is the independent variable. So we get 0 for the first term. The next term is going to be cosine pi x plus 3y minus z. But the derivative of the inside is negative 1 because you're only looking at this z term. So there's a negative 1 right there. And then you do plus, and then there's the 2 over ln 10 thing. And then you have 1 over xy plus yz plus xz. The derivative of the inside, since only z is a variable, you're going to get y plus x here. And the last term is 1 over 1 plus xyz squared. And the derivative of the inside is simply xy. So these answers are very symmetric looking, and that is sometimes the case when you do partial derivatives. Your answers look quite similar. Notice that you can't really ask what is the derivative. You have to ask what is the partial derivative with respect to whatever. Okay? So it doesn't make sense to ask one derivative question, what is the derivative? There's 3 of them here. Okay, this leads us to the last problem. What do we do if we just don't want to isolate z, or maybe we can't isolate z? Okay, so if that happens, let's say you're trying to find the derivative here. You need to know which derivative. So we're going to be finding dz dx on this. And we could also do dz dy, but that's probably a little overkill. Let's just do one of them. Okay, so to find dz dx, you're just going to start doing an implicit differentiation. So x is a variable, y is a constant. See? And z, we won't assume z is a constant. We don't want to, because if we could somehow isolate z, we would expect to find x's in that function. So we can hold y as a constant, but we can't hold z as a constant. We're going to have to use a chain rule whenever we hit a z. So first we'll start with xy e to the z. We'll try the derivative of that first. So the x is a variable. Let's write it as xy times e to the z. The x is a variable. The y is a number. So we're going to do like a first function derivative times e to the z plus second function's derivative times xy. So it's going to be basically a product rule like this. So first we take the derivative of xy, and that gives us y. We leave the e to the z there. Then we leave the xy here, and we take the derivative of e to the z. So the derivative of e to the z is e to the z times dz dx. We need the chain rule because we don't trust z to be independent of x. We only hold y constant here. That's the left side. The right side is 3 sine xz, you see. So we'll leave the 3 there. We'll definitely have a cosine here. We still have an xz here because that's our angle. But now we need to multiply by the derivative of the inside. So the derivative of the inside, xz, you have to think of this as x times z, right? And then you're going to think of x as your independent variable, z as dependent on that. So you have to do a product rule. So the derivative of this is going to basically be the derivative of x with respect to x times z as is plus x as is times the derivative of z, like this. So you basically get z plus x dz dx. You should use those curlies, not the regular d's when you do the partial derivative symbol. Okay, now we have to isolate dz dx, which is a matter of distributing, bringing all the terms out of dz dx to one side, and then isolating by dividing. So I'm just going to write my final answer. So the final answer is y e to the z minus 3z cos xz all over 3xz cosine xyz, or sorry, xz, minus xy e to the z. Make sure I copy that right. Yeah, that's correct. So notice the top and bottom are kind of symmetric to each other. They're very similar numerator and denominator there. If you want to find second derivatives or third derivatives or so on, basically, if you want to find second derivatives and you're in 2 dimensions, there are actually 4 possibilities. fxx, which means you'll take the derivative with respect to x twice in a row. fyy, which means you'll take the derivative with respect to, y twice in a row. And then we have mixtures. So like fxy would mean first you take the derivative with respect to x, and then you take the derivative with respect to y. Notice it's read left to right. xy means first differentiate with respect to x, that's on the inside, and then differentiate with respect to y on the outside. So y is last. So probably should have circled x and y in red and green there, okay? And the last possibility is the fourth case, where you take the derivative first with respect to y, that's on the inside, then with respect to x. So you read it left to right, and you do it in that order. If you seek third order partial derivatives, there's actually 8 possibilities, and for fourth order there'd be 16 and so on. So if I say, hey, find the partial derivatives, and I give you, or the partial third order derivatives, that means the third derivatives, and I give you a function that has x and y in it, like z equals x squared y, and I say, hey, find the partial derivatives, there's 8 of them. If you're doing third derivatives, sorry, find the third order partial derivatives, there are 8 of them. If I say find the fourth order, there's 16 and so on.